A careful examination of the objects in the solar system provides convincing evidence that the Earth and other planets are each unique worlds with unique characteristics. In Lecture 35, I want to take you on a tour of the solar system. We're going to start nearest the Sun with the swift, tiny planet Mercury and work our way outward to the cold, dark, distant world of Uranus and Neptune. I love this subject. Earth and other planets are each distinct, each is different, each has its own personality and idiosyncrasies. Each planet holds surprises. Each planet is begging for more research, begging for more discoveries. There's always a danger, of course, with 9 planets and dozens of moons, that such a travelogue might begin to seem overwhelming. It's like visiting 13 European cities in 14 days and trying to remember which cathedral goes with which city. It's almost impossible after a while. So I'm going to ask you to remember just a couple of words or a couple of phrases to associate with each of these planets, each of these worlds. I'm going to emphasize the similarities of the planets as well as their differences as we go along. So let's go on this travelogue. Oh yes, I've been remiss. I haven't told you about another teaching company course which you really should see if you like the subject of astronomy and cosmology. It's Astronomy, An Introduction to the Universe by Alex Filipenko of Berkeley. Well, as we embark on this tour, keep in mind how the solar system formed from a nebula of dust and gas. It began as an irregular cloud of dust and gas just sort of floating around, but perhaps a shock wave from a supernova created dense local areas, and those dense areas became the focus of gravitational collapse. As the dust collapsed, it began to rotate faster and faster, forming a flat disk with a bulging center, and other dust spread out. The central bulge became the Sun, the flat disk became the planets. The Sun ignites, it sends out heat, it sends out solar wind, and that strips the inner planets of the hydrogen and helium, so you have 4 inner terrestrial planets. And then you have 4 larger Jovian planets, or gas giant planets farther out, made primarily of that hydrogen and helium that's been pushed out in the outer reaches of the solar system. In this lecture, we're going to examine these planets, the planets that make up the 4 inner terrestrial, the 4 outer giant planets. I want to make a key point here. We live in an absolute golden age of astronomy, a golden age of planetary exploration. Planetary probes by NASA and other agencies have now visited every planet except Pluto. We have, in the last quarter century, learned more about these worlds than in any previous time in history. Astonishing close-up photographs of alien worlds. We've discovered new moons, many unsuspected features of these closest celestial neighbors, the planets. Never before in history has the pace of discovery been so rapid. And because of NASA's public outreach, because of their educational policies, every one of us can share in this exploration as it's happening. It's all on TV. It's live on the internet. All you need to remember is www.nasa.gov. Okay, to our travelogue. The innermost planet is Mercury. When you hear the name of Mercury mentioned, I want you to remember 2 words: blasted and dead. Mercury, the innermost planet, is a desolate, it's a forbidding world. Its small size and its proximity to the Sun have made Mercury extremely difficult to observe, at least with Earth-based telescopes. Mercury's elliptical orbit takes it as close as 43 million kilometers to the Sun and as far away as 70 million kilometers. But even so, it's much too close to observe clearly against the bright light of the Sun. The swift orbital period of Mercury is just 88 days. And surprisingly, a day on Mercury lasts twice that long, 176 days. So on Mercury, the day is twice as long as the year. Our knowledge of planet Mercury was greatly enhanced by the Mariner 10 spacecraft, the only spacecraft so far to fly near Mercury. Photographs reveal a heavily cratered surface. It's alternately baked to 500 degrees centigrade on the sunny side and frozen to minus 200 degrees centigrade on the dark side. Mercury has no atmosphere whatsoever, and thus there's no erosion to wear down the deeply cratered and pockmarked surface. The poles on Mercury are extremely interesting places. That's because the planet's tilt is absolutely zero. It's locked in at zero by the sun. Thus, the poles are in eternal twilight with the sun grazing across them. It's possible then that the temperature in some places at the poles are right around the boiling point of water. It's even possible that some places near the pole there may be reservoirs of liquid water near the surface. So I suppose I could be wrong. It's possible that Mercury isn't blasted and dead. There might even conceivably be some form of life at the poles. Nevertheless, I want you to remember two words with Mercury, and that's blasted and dead, until we know any better. Several scientists, by the way, are proposing missions to Mercury to place a spacecraft actually in orbit around Mercury early in the 21st century. Such a mission would be exceptionally complicated because of the orbital dynamics. Think about this. You have to send a spacecraft very close to the sun, and you don't want that spacecraft to fall into the sun. You want to go around orbit of Mercury. And not even in the normal orbit, but you have to get it into a polar orbit. So you have to take a huge amount of fuel to make those orbital corrections, and almost all the weight that you carry with you then has to be the weight of fuel. It's very hard to get scientific instruments into orbit around Mercury. In addition, the entire spacecraft has to be shielded from the sun's radiation, so you have to carry along a huge sunscreen, and that screen has to always point towards the sun or your whole mission will be destroyed. Now, second planet, Venus. Venus is our nearest planetary neighbor, both in distance and in size. And when you think of Venus, I want you to remember two phrases, Earth-like and greenhouse effect. The orbit of Venus is nearly circular. It has an average distance from the sun of 108 million kilometers. It has an orbital period of 225 days. That's about 2/3 of Earth's year. Venus also, as I mentioned last lecture, has a slow retrograde rotation about its axis. It actually rotates the wrong way, if you will, and the Venusian day is 243 Earth days. So once again, the Venusian day is slightly longer than the Venusian year, a strange situation. That retrograde rotation, by the way, is thought to be the result of a late-stage collision that occurred when two bodies were competing for the Venus orbit. The smaller one hit Venus. It didn't destroy Venus, it just made it start rotating the wrong way. Venus is enshrouded in a very thick atmosphere composed primarily of clouds of carbon dioxide and of nitrogen. The daytime surface temperature reaches almost 500 degrees centigrade as a result of an exaggerated greenhouse effect. Now, the greenhouse effect you've experienced if you've ever done gardening in a greenhouse in the wintertime. Sunlight comes in, it heats up the ground, it heats up the plants and the soil, and that heat energy is trapped by the greenhouse. In the same way, carbon dioxide on the Venusian atmosphere traps sunlight, and the planet gets hotter and hotter and hotter, in what's called a runaway greenhouse effect. The surface pressures are tremendous. Beneath the thick atmosphere, it's supposed to be about 95 times the pressure of that on Earth's atmosphere. That's about 1,400 pounds per square inch pressure at the surface of Venus. Though that surface is forever hidden from our view, at least with telescopes, the Venusian landscape has been mapped in detail by orbiting satellites around Venus that look at the surface with radar. The radar maps show a planet with mountain ranges. They have cratered plains, ancient volcanoes. In fact, evidence of a once active planet, though not quite so rugged and not quite as dynamic as the Earth is today. Still, Venus is very Earth-like. The Soviet Union succeeded in a tremendous technological feat when they had 4 Venus landers, Venera 9, 10, 13, and 14. These all returned remarkable surface photographs of a rocky landscape. So, remember, Venus might have been a lot like Earth one day if it hadn't been for that intense greenhouse effect. I'm going to skip Earth now because that's the subject of the next several lectures, but we now go to the 4th planet, the red planet Mars. And it's by far the most intensively studied of all our solar system neighbors because of the strong possibility that it once had abundant surface water. By all theories, life is absolutely dependent on water. And if any nearby planet harbored life, then Mars is the odds-on favorite. Well, call me an optimist if you will, but when you think of Mars, I want you to think of 2 words. Cross your fingers, Click your heels together 3 times and think water and life. Well, Mars is about half the diameter, only 11% of the mass of Earth. It has an elliptical orbit that averages about 1.5 times the Earth-Sun distance. As a result, Mars can be as close to Earth as 60 million kilometers, and that's not very far away by solar system standards. It can also be as far away as 400 million kilometers. Excuse me, 400 million kilometers, yes, excuse me. A year that is 686 days long is almost 2 years compared to Earth's 1 year. A day on Mars is coincidentally very close to 24 hours. And that could be a great advantage to future colonists if we ever decide to colonize Mars. Mars is tilted about 20 degrees on its axis, and that tilt causes seasons on Mars very similar to the seasons on Earth. Again, this could conceivably someday be an advantage if we ever colonize Mars. Mars has 2 objects in orbit around it. They're really too small to be called decent-sized moons, but Phobos and Deimos look sort of like captured asteroids. They're just tens of kilometers across, but they are moons nonetheless by that sort of definition. Now, unlike Mercury and Venus, Mars has surface markings, and these are easily and clearly visible from Earth. Remember, Mercury is too close to the Sun, so we can't see it with our telescopes. Venus has a thick atmosphere, but Mars has very little atmosphere, and we can see those markings prominently with our telescopes. And most obvious are the polar ice caps. These ice caps wax and wane with the 686-day Martian year. The planet also shows brighter and darker patches on the surface, reddish areas that appeared to some 19th century astronomers as linear features. In fact, the American astronomer Percival Lowell, who lived from 1855 to 1916, used a new observatory in Flagstaff, Arizona to draw and to study Mars, and he interpreted these lines as artificial canals used for irrigating the dying planet. Lowell published detailed maps of more than 500 canals, and he said that the extensive network, quote, points to an efficient government. Well, that's quite an extrapolation for Lowell to have made. We got a much better look at Mars with the Mariner spacecraft missions in the 1960s, and these returned the first close-up pictures of that spectacular Martian surface. We see natural water-carved valleys. We see cratered plains. Huge volcanoes are also observed. We see extensive systems of what appear to be braided streams, water-worn valleys on the surface of Mars, and suggest that Mars once had abundant water and perhaps a much thicker atmosphere than today. Well, think how Mars must have changed in the last 4.5 billion years. There were volcanoes once. Those volcanoes brought water to the surface, H2O, in the atmosphere, which must have rained down and caused streams and lakes and other sorts of surface water. So where did all that water go? It turns out that at less than half of Earth's gravity, water molecules can escape into space. This is a very slow process. It's a gradual process, but it's an inexorable process. And so the water that was once on Mars' surface has probably just escaped, slowly evaporated away. Viking lander missions of the 1970s returned pictures of a dry, barren, blasted world, a desert world. The pressure of the carbon dioxide atmosphere is only 0.5% of Earth's atmosphere. Even so, there are intense dust storms that blast the surface with winds over 100 kilometers per hour. They scour the surface over and over again. The most spectacular Mars mission so far was the Mars Pathfinder mission, which touched down on July 4th, 1997. It featured both a lander and a 6-wheeled, 23-pound rover named Sojourner. The mission returned spectacular 3-dimensional pictures of the surface and also had chemical analyses of the rocks, which turned out to be very similar to Earth rocks. The red color of Mars comes from iron oxides, for example, very common on the Earth's surface. It also verified that the atmosphere is mostly carbon dioxide, though much less pressure than on Earth's surface. NASA is already planning a sample return flight for 2005, and my laboratory is eagerly awaiting those samples, as I mentioned last time. They also hope to deploy a manned flight, perhaps sometime by the year 2020, and wouldn't that be an incredible thing to see men and women walking on the surface of another planet? on beyond Mars. We come to the asteroid belt, which is a broad band of rocky debris halfway to Jupiter, just about where you might expect to see another terrestrial planet by the spacing of the planets. There are perhaps 50,000 objects that are a kilometer or more in diameter. And your key phrase here for the asteroid belt is big rocks, because that's what they are, a whole bunch of big rocks out there. According to one theory, the strong gravitational force of Jupiter prevents these objects from ever clumping together to form a planet. Now, occasionally, there are going to be Earth-crossing asteroids. These are asteroids that are in very elliptical orbits that come inside the orbit of Earth and out. We now see on Earth's surface numerous prehistoric impact sites, which clearly show that some of these asteroids from time to time hit the Earth. Indeed, we now have strong evidence that an asteroid that was perhaps 20 kilometers in diameter hit the Earth near what is the modern-day Yucatan Peninsula of Mexico. That was about 65 million years ago. That epic blast resulted in the extinction of the dinosaurs and many, many other groups of animals and plants. Some scientists, including the American astronomer Carl Sagan, have suggested that these Earth-crossing asteroids pose a serious potential threat, perhaps the most serious threat to the survival of the human race, and that they should be mapped in much greater detail. Furthermore, he says we perhaps should develop a space presence, a mean to deflect such an asteroid if it's ever shown to be coming towards our planet. Okay, to the Jovian planets. The character of our solar system changes radically beyond the asteroid belt. This is in the realm of these gas giant planets. Jupiter, the largest of these giant planets, is a ball of hydrogen. It's 2.5 times as massive as all the other planets combined. It could have been a star, but not quite. Whenever Jupiter comes up in conversation, I want you to think two things: weather and amazing moons. First, think about what happens to balls of hydrogen in space. That is, any object that's gravitationally bound just from gas and dust in space is going to be primarily hydrogen with some helium. So all sorts of objects occur out there, from small ones to large ones. If they begin 10 times the mass of the sun, they end up as exploding stars. If they begin about the mass of the sun, then you go through the hydrogen burning phase, then become a red giant, then a white dwarf, and sort of dwindle away their life. If they begin a tenth the mass of the sun, they end up as brown dwarfs, stars that can burn for hundreds of billions of years. And if they begin 100th of the mass of the sun, if the ball of hydrogen has only 100th the mass of our sun, you end up with a big planet. Because nuclear fusion never gets started, you just have that big ball of hydrogen and helium and other atoms. Jupiter is about 5 times the Earth-Sun distance. It orbits the sun every 12 years. A day on Jupiter, though, is only 10 hours long. Now think about that. Jupiter is a much, much larger planet than the Earth, and yet it orbits once every 10 hours. It's spinning so fast that it bulges at the equator. It also causes intense and violent weather. Weather, that's one of the 2 words I want you to remember about Jupiter, because when Jupiter rotates, it shears its atmosphere of hydrogen and helium into many, many bands and layers. You have intense vortices spinning where these atmospheric bands come in contact. You have giant storms, immense storms, bands and swirls that you can see with the various close-up photographs we've taken. The largest of these storms is the Great Red Spot. It would swallow 100 Earths without even missing them. A lot of our detailed knowledge of Jupiter has come from space probes, notably NASA probes such as the Voyager spacecraft, also the Galileo and the Ulysses probes. These missions have returned spectacular photographs of Jupiter's surface, and they accumulate a huge amount of data on the composition, on the magnetic field, on the unexpected dynamic moons. Here are some highlights. First of all, Jupiter has intense weather in its 1,000-kilometer thick atmosphere. The Great Red Storm, for example, is a storm that has been raging for over 300 years. And by the way, that red color now apparently is due to carbon-based organic molecules, molecules that may have been created through lightning storms, which are abundant also in the upper atmosphere of Jupiter. The atmosphere appears to be about 79% hydrogen and 20% helium, plus that maybe 1% of organic molecules that gives it the bright colors. Jupiter has a magnetic field, and that magnetic field may be 10 times stronger than Earth's. They think it might be generated in an interior region because of metallic hydrogen. At very high temperatures and high pressures, hydrogen, as all the materials, is going to become a metal. And electrical currents may flow in that metal and create the great magnetic field. Astronomers have identified 16 different moons of Jupiter, ranging in size from asteroid-like bodies just 20 kilometers across to the giant planet-like Ganymede, which is 5,200 kilometers in diameter. It really is like a small terrestrial planet. If scientists were asked any place in the solar system they'd like to visit first, many of them would put Jupiter's 4 largest moons right at the top of the list. That's why I want you to remember amazing moons when you think about Jupiter. The 4 of these large and interesting moons are called the Galilean moons. Those are the moons that Galileo saw in his telescope in 1609. It includes Io, Europa, Ganymede, and Callisto. Galileo made drawings of their movements, and we now know that each of these objects, although they look similar in Galileo's telescope, each of these objects is distinctive, an own world in its right, in many respects like terrestrial planets. They differ in size, they differ in composition, they differ in their dynamics. Io is the innermost of these large moons. It's almost as large as Mercury. It has its own atmosphere. It has extensive volcanism. In fact, Io is the most volcanically active place in the solar system. It's so close to Jupiter, it turns out, that Io experienced severe tidal forces which stress and bend and break the moon. And that's what pumps the energy into Io to keep it so volcanic. Europa. Europa is the second moon of Jupiter. It's the smallest of the Galilean moons, but by far the most interesting. Its surface is covered by what appears to be a cracked sheet of water ice, water that may cover a thick ocean. If tidal stresses from Jupiter keep this ocean warm, then Europa may actually harbor the most Earth-like environment anywhere in the solar system. So NASA is very excited about studying Europa some more. They plan an orbiter mission for early in the 21st century, and then altimeter studies measuring the distance to the surface will be able to see if the planet's stressing and bulging, to see, in fact, if the liquid ocean is there, because a planet bulges more if it has a liquid ocean than if it's solid. NASA also hopes to follow this up with a lander and possibly even an ocean probe thereafter. Now, this results in NASA's current interest in the Earth's ocean. By studying the Earth's ocean, NASA is gaining experience in how to put deep probes at the bottom of the ocean and collect measurements. So you may see NASA supporting oceanographic research, a strange idea, but not at all strange in the context of the Europa exploration. Then we have Ganymede, Jupiter's third and largest moon, and Callisto, which both have worn, cratered surfaces. These suggest long periods of geological inactivity. Even so, there's a possibility that Ganymede, too, may have a deep inner ocean. Another exciting moon to watch. Voyager found several other moons, varying in size from a few kilometers to much larger. They also found a series of thin rings around Jupiter, which turned out to be a common feature of all the gas giant planets. My favorite planet by far is Saturn, which is the second largest planet. It has the breathtaking rings. And your 2 words to remember for Saturn are rings and Titan. You can see the rings with a good pair of 10-power binoculars. Now, at about a third the mass of Jupiter, Saturn is very, very similar in character to Jupiter. It's just less massive. It's also primarily hydrogen with a little bit of helium. It also has severe weather patterns. It also has a 10-hour rotation period, which streams out the atmosphere into bands and bulges the planet. Saturn is about 10 times farther out from the sun than Earth. It takes almost 30 years for Saturn to complete an orbit around the sun. And so it's fairly easy to keep track of Saturn from year to year. It doesn't move much in the night sky. The ring complex is so magnificent. It's actually a complex of many, many little ringlets which appear in detail like the grooves of a record. The dynamics of this fine structure are absolutely fascinating. Here you have a structure composed of thousands of millions of countless particles, tiny particles. And detailed photographs from Pioneer and Voyager 2 show that these rings are also made of water ice, little bits of rock that are coated with ice, and they're herded into line by a series of tiny satellites, perhaps a kilometer in diameter, that keep all the smaller particles in line. Astonishingly, that ring is extremely thin. The thickness of Saturn's rings may be no more than a few tens of meters, even though they're thousands of kilometers across. Now, given the nature of Saturn's rings, it's rather difficult to tell exactly what to call a moon. Astronomers have identified about 20 objects that are greater than 15 kilometers in diameter, and maybe that's a reasonable definition. While most of these are irregular, asteroid-like bodies, the largest moon, Titan, is a uniquely fascinating world. The name Titan is really worth remembering because when you think of Titan, you think of the largest moon, the most unique moon in the solar system. So when you think of Saturn, think of Titan. Titan is larger than Mercury, although it's only half as massive because it's about half ice and half rock, and Mercury is a solid, rocky terrestrial planet. Titan has a substantial nitrogen atmosphere. In fact, its surface pressure is about 1.5 times Earth's atmosphere, so that's a pretty significant atmosphere on Titan. Voyager 1 photographed Titan and found that the surface of the moon is obscured by an orange smog, and that orange smog is made of carbon-based compounds. So here we have organic compounds, an atmosphere that's similar, at least in pressure, to Earth's, a fascinating world to think about. Nevertheless, the surface of Titan is quite cold, it's frigid, and so it may actually be covered with lakes of liquid nitrogen and methane and ethane. Someday, travelers in the solar system might actually stop by Titan, mining or collecting fuels for their voyages in deeper space. Now we turn to the outer two planets. Uranus, discovered in 1781 by the celebrated English astronomer William Herschel, who lived from 1738 to 1822. In fact, when you hear the name Uranus, I want you to think gas giant and the Herschel family. The Herschel family was an amazing family of astronomers. William Herschel was born and raised in Hanover, Germany, but went to live in England with his father as a teenager and remained there owing to the French occupation of his hometown. The young William was trained as a musician. He was an organist, he was a conductor, he was a composer in the resort town of Bath in England. But he loved astronomy, and as an amateur he built beautiful, superb telescopes. And with one of these telescopes he discovered the planet Uranus in 1781. This won him a pension from the Hanoverian king, George III. This generous annuity allowed him to devote full time for the rest of his life to astronomy. His large and magnificent telescopes allowed him to observe and catalog more than 2,500 star clusters and galaxies. He also studied binary stars and cataloged them as well. His sister, Carolyn Hershey, aided in these studies, and she was a distinguished astronomer in her own right. She began as a singer, a musician also, but like her brother, she switched full-time to astronomy once the king's pension had been granted. She contributed the most detailed and comprehensive star catalogs of the day. And then John Herschel, his son. John Herschel went on to become one of the great astronomers of the 19th century. He became a scientific icon of his day, much like Albert Einstein or Stephen Hawking in the 20th century. The younger Herschel, for example, introduced photography to astronomy in 1839. He's the guy who invented the names negative and positive in association with photography. He made pioneering telescopic observations in the southern hemisphere. He did all sorts of things, cataloging binary stars and nebula and so forth. Well, all this family history was triggered by the discovery of Uranus. So when you think of Uranus, think of the Herschel family. Uranus is about 19 times the Earth-Sun distance, has an orbital period of 84 years. The planet's 4 times the diameter of Earth, and it's 100 times more massive than the Earth. Voyager 2 flew by the planet and revealed that the Uranian day is about 17 hours. The rotation axis of Uranus is very strange. It's on its side, so the planet's orbiting with one pole pointing towards the sun and one pole pointing towards away from the sun, the only planet to do this. Of course, like the other gas giant planets, it's composed primarily of hydrogen and helium. Uranus has 5 major moons, all of which appear to be frozen and inactive, as well as a complex system of rings. And then the 8th planet, Neptune. A discovery of Neptune was a triumph of Newtonian models because its existence and its approximate location were predicted by the perturbations in the orbit of Uranus. It was done independently by astronomers in England and in France, and then was discovered by French astronomers in 1846. When you think of Neptune, think of the words gas giant and blue. Neptune's is 30 times the Earth-Sun distance with an orbital period of 165 years. It takes light 4 hours to travel from the Sun to this distant planet. Most of our knowledge comes from Voyager 2, the NASA flyby in 1989, which photographed the beautiful blue planet. It has a frigid, hydrogen-rich atmosphere laced with methane. It's 60 degrees above absolute zero at the surface. The great dynamic weather patterns are driven by a 16-hour rotation period, so it's not unlike Jupiter and Saturn in that regard. Neptune also has several moons. It has a ring complex. And the largest moon, Triton, is an important world. It has its own methane-rich atmosphere. Well, I know that's quite a trip. To summarize, we visited 7 planets and quite a number of moons, as well as the asteroid belt. And I've covered a lot of detailed ground, but I've asked you to remember just a few key words and phrases, 2 for each object. Remember Mercury, blasted and dead. Venus, Earth-like and the greenhouse effect. Mars, water and life. Asteroid belt, big rocks. Jupiter, weather and amazing moons. Saturn, rings and Titan. Uranus, gas giant and the Herschel family. Neptune, gas giant and blue. Well, ultimately, why should we care about the physical and the chemical characteristics of these and other planets? In part, our fascination arises because planets are such beautiful and complex systems, and because they played such a rich part in the history of the human race. But to many scientists, the planets hold the key to understanding our own world, our own dynamic world, and that is the subject of the next lecture.